industry, and they said if the auto industry had kept pace with computers, we'd all be driving cars that got 200 miles to the gallon, and so forth and so on and so forth. And GM's response, allegedly, which is, it's been Snopes out, it's not true, but GM's response is, yes, if we built cars like Microsoft built computers, they'd also crash 3 times a day with no reason. We'd have to stop, pull off to the side of the road, unplug the battery, plug it back in, everything would be fine. And they had this whole laundry list of awesome analogies to computers that were genius, absolutely genius. So Google that one, it's a fun one. It's bogus, but it's hilarious. So anyway, how are you? Good? Week 6. Wonderful. That's good. So how was that? How was that project? Terrible.
Horrible.
Horrible. Worst thing you've ever done.
It's like a slap in the face compared to the last one.
Yeah. Well, okay.
I mean...
Wow, fine.
If you... I didn't mean to have facial slappage. I did not mean that to happen. What I meant was to just take the next logical step, which is sampling more than one thing at a time, which is kind of where we're actually kind of heading today too, and the rest of the course actually, the next 4 weeks together. I apologize for that. And actually, talking to some of your classmates in the other 243 class, I have some, unfortunately I thought of this yesterday, but I have some other ideas of ways to kind of link video stuff into it that would give you another way to look at it. When you said, Kate, about how I talk versus writing, I started thinking about that more and more, and I haven't put any video links per se in any of the projects yet. They've all been video links in homeworks and in the class lectures and sometimes just addendum videos, but I think projects are a good place, especially something like this maybe. So, it won't help you guys, I apologize. If I can get something in the last 2 projects maybe, in the last 2, I hope I can do that.
After everybody checks in, could we like ask questions?
You can always ask questions on them, but...
I mean like, could we like go over some of them like after everybody went in? Because I know that I got a couple wrong and I didn't have a chance to go ask anything.
You mean like you couldn't get the number? I'm showing you couldn't get the number I was telling you to get?
I tried every single one of them and I'm like...
Well, the problem with this, and I think this goes to what Hattie was saying, the problem with these, I gave you all the numbers you needed, essentially. Like, here's what the answer is, here's what the answer is, here's what the answer is. There's not much, you could try many different approaches to getting those numbers, but if you're kind of like, just trying, like, let's just try this, let's try subtracting 1, subtracting 2, subtracting 3, there's like infinitely many ways to try, and that can drive you nuts trying to do that.
I was just like, trying to like apply that to the other ones that you would, your examples, and using the formula.
And they tie perfectly in.
Yeah, and I was getting them wrong, and that's why I was really frustrated because I'm like,
you just weren't, you weren't seeing the connection. Now, part of it too, and I didn't realize this till yesterday talking with somebody, if you round incorrectly in the intermediate steps, you'll get further and further away from the final answer, and then be like, he's getting 58.6% and I'm getting 52.4. And you're doing the right math, but you're rounding every step of the way. This can happen. I saw it happen yesterday actually, where somebody's rounding incorrectly as they go. They're doing the correct math on the wrong number and getting, therefore, an incorrect, correctly worked answer, which is frustrating.
I'm because I'm like,
yeah.
trying different ones.
Right. But my point is that it's not that you're not doing it right. It's that something outside. Skylar, when you just said, I'm trying to graph this, and I can't get the same thing to graph because I'm getting an error message, the error she was getting was not related at all to what she was doing. It was something unrelated that was causing the error, and that's oftentimes what happens on these. That's why I beg you to contact me before they're due, and we can walk through it. I mean, usually sitting down with me for 5 minutes, we can figure out what the problems are. So, again, next one's not due for a couple weeks. Next one is got a lot of Excel component to it. I call it simulations and super counting. Quite a bit of statistics these days is done via mathematical simulations, or computer simulations of mathematical occurrences, and we're going to see a couple of those today. That's one of the reasons I gave you the dice, is because we're going to compare and contrast what you're holding in your hand with what Excel can actually do. So you can always ask me questions. Just make sure that give yourself enough time to work through them, so you're not under the gun and feeling pressured. Because then you can't think straight, you can't think clearly, and it drives you nuts. I don't want to drive you nuts any more than I already do. I know I do that already. So anyway, next project's not due for a couple weeks. Let's chit-chat about the next week. I think you have your next in-class exam, yeah? I think a week from today. And we'll talk, I think, right? Week 7, I think. Pretty sure. And I'll have an out-of-class posted this weekend at some point. Don't go to your classes on Monday. At least your COCC classes. I just found out that OSU is not honoring Veterans Day. Oof. Ouch. Yeah, owie.
What?
Yeah,
No
yeah.
state
A
schools
little upset about that myself. But anyway, no COCC classes on Monday. That doesn't affect you guys and me. Thankfully, that wouldn't issue. But I'll have an out-of-class exam posted for you on probably on Sunday, and it won't be due till like week 8 sometime. It'll be due way back. I try to do that so you have it in class, and then you have like 5 more days to turn in the out-of-class part. So you have plenty of time to slow through it and use Google, use your friends, make study groups, whatever you got. Ask me questions, of course. Of course, it'll have an Excel component like the last one did, because Excel's good and you should learn how to use it and play with it. And I was a little bit goofy. Remember when I said we finished up outliers last time, and then I said don't bring questions next class. Bring them Tuesday. Because you had so much stuff, this pile is testimony to how much stuff you had to do today. I seemed kind of unfair to have you have homework, a quiz, and a project. So we'll do 2 quizzes, potentially, right? 2 quizzes. Yeah, that's right, there were 2, potentially. Although the outliers one you can turn in next week if you want to, as well. So Tuesday, let's start Tuesday by going over a bunch of questions. Outliers, and also, this is going to suck a little bit, and I apologize, but outliers and probability distributions, which is what we're in the middle of right now. We're in the middle. We started that in class on, whatever the hell last class was, Tuesday. And we're going to do that. That's all we're going to do today is that idea. The idea of taking probabilities and putting them into t-tables and then analyzing the t-tables and seeing what we can get from them. And hopefully what you get from them today is the ability to fuse statistics into probability. That's my big idea for today. And also so you can understand your insurance policies, and also so you understand what you're getting into when you walk into a Vegas casino. That's all related to the big idea of distributions of probabilities. Yeah? If that doesn't make any sense right now, I'll give you an hour and a half, and we'll hopefully get you some questions later. It'll make sense. Okay, we're done. So I just mentioned the phrase probability distributions. Remind me about this. Remind me what that is, or what they are, or why we should care about them. You can skip the why you should care about them part. Hopefully we'll answer that in the next hour and a half. What is it? What were we doing last time with it? We're handing dice out. We're handing dice out. Thank you, Isabel. Much appreciated. We're handing dice around. You're all grabbing dice. Last time I gave you 2 dice, we only used 1. What did we do last time? What did I ask you to do? Roll it a bunch of times and keep track of what you got. Jenny got 6s, 3s, and 1s. And we collated all the results. And what did we do with all those results? Do you remember? It's okay, it's a long day. It was 48 hours ago. Say that again. We made a table, didn't we, Jamie? How many columns did the table have? It started out having like 6 or something, right? But we eventually diluted it down to how many? Eventually, because we started with this one. If I remember correctly, it all started with x equals the number of pips.
Yeah.
The pips that we're showing. It all started with that, and we called that 1, 2, 3, 4, 5, and 6 for a single die. And do you remember the fancy trade name for what x is? It's a fancy little name. I think I may have said it, but I written it down, and I apologize if that's the 2 words.
The random variable.
Okay, good. At least mention it. The random variable. And why do we call it a random variable? Jenny, I think you defined it for me if I remember in class. We call x a random variable. Why is the word random in there? Why is the word random in there?
You don't know which one to leave, and it'll be fine.
Boom! Good. And the definition of a random variable is something that is somehow dependent on chance. It's a value, a numerical value, somehow dependent on chance. And the reason it's somehow, as Jenny just pointed out, is you're going to throw the die, and you are going to get 1, 2, 3, 4, 5, or 6. You're only going to get one of them. You can't get more than one of them. The chance part is you don't know which one you're going to get. So you know you're not going to get 8, you're not going to get -7, you're not going to get 200. But you're not sure if you're going to get 2 or 3, or 6, or 5, or 4, or 1. Beautiful, beautiful. And then we made a bunch of columns. We had a frequency column, relative frequency column. We kept going and kept going and kept going. We had the empirical, the experimental frequency. We're going to come back to that today too. And the very last column, the theoretical. And I even changed the name to the probability of x column. P of x. And all that meant, it looks terrible. Looks like Math 111, I know. But all that means right there is what's the chance that x takes on the value that's over here. That's all that meant. And what were those theoreticals for a single die? Every single one of them, right? 1/6. I got some people testing me back there. Excellent. 1/6, 1/6, 1/6, all the way down. Theoretical. We're assuming that each one of the 6 sides of those dice are just as likely as any other of the 6 sides of those dice. So it should be 1/6. We didn't get exactly 1/6 on our percentages, did we? Did we get close enough to believe it? Yes, we did. We did. Even though we had a spike, I think it was at 1 and 3. I don't exactly remember what. We had some percentages that were too high, like up near 20 and 21%. But with a sample size as small as we had, that's arguably the same as 1/6. Or said a more 244 way, there's no reason to think it's any different than 1/6, even though it's a little high. So when you read a Gallup poll, and the Gallup poll says Obama's approval rating dropped 1 percentage point between last week and this week, and the margin of error is 3%,
Doesn't really matter.
you say, you can't claim that it dropped if the margin of error is bigger than the change. Because if it only moved 1 percentage point, that's still within the margin of error of 6%, 3 up and 3 down. You see what I'm getting at there? That's why our margin of error, which I didn't have you calculate in class, was very, very large, because we only had like 200 trials or something like that. We would have had probably a 4 to 5% margin of error. So when we came back with 20% ones, that could have been as low as 15 or as high as 25. 1/6 is in that range, so there's no reason to think it's anything different than 1/6. We haven't disproven 1/6 by our data. Does that kind of make sense? I'm getting a little 240 on you here, but we've also seen it enough, I think, in here to kind of understand that idea that you build an interval around the estimates. These don't have intervals. The theoretical probability of throwing a die is 1/6, because there are 6 sides that are all the same weight. Therefore, when you throw it, you've got just as much chance as one as the other. Is that believable? Awesome. Beautiful. What did you notice when we added all these up? Uh-huh. Why is it 1? Well, it always sum to 1. Will it always sum to 1? I should say that, of course, because 5, 6, 1, 6 always sums to 1. If I create a distribution for any other experiment, which we'll do 3 times today, will they always sum to 1? They have to. Tell me why. 100% of the time, we're going to get 1 through 6 in this case. So assuming you've set this column up correctly, this is everything that can happen. And 100% of the time, you're going to get something in this experiment to happen. Thanks, guys. Perfect. Perfect. Cool so far? Let me ask a question. What's the average number of pips that you get when you throw a die? Did we answer this question on Tuesday? We might not have. Megan's saying no. And we may have conversationally talked about it but not gotten into it. What's the average number of pips that you would get if you throw a die over and over and over and over? Because that's the idea of an average. If we had to share all the pips, what would we get? Michael, vote?
3.5.
Votes for 3.5. Kate seconds the vote for 3.5. Scott third. Fourth, yes? All in favor? All opposed? Discussion? Yeah, we can discuss this. Where'd 3.5 come from? Where'd 3.5 come from? Good question. Okay, good. Now, Kate said you add them all up and divide by 6. I like that in this case, because it will work perfectly. I don't like it in general. So I'd like to approach it a different way that'll work in general, if that's okay. Now, one way you can work it is run it through your TI. And we will do that today, I promise you. I promise you we'll do that today. But today I'm also going to revert back to what we've always done in the past, which is what kind of an average. This is set up for a special kind of average that we've talked about in the past. Because you have an X column and essentially a frequency column, what kind of average should we take? We haven't talked about it in a while because we've gotten away from it because we're talking about things like quartiles and... JC?
Mean.
What kind? I love it. It is the mean. Starts with a W.
Weighted.
Boom. There it is. Say nice and loud. Patty, it's a weighted mean. Now, the reason why I said I don't care about this particular case because the weights are all exactly, the weights are all equal.
Well, that's why I told you how to do it this way.
And that's why I thank you. Right? That's why I thank you. And if it's a symmetric distribution, it doesn't matter either. The differences do occur when you have to look at the standard deviation and if they're highly skewed distributions, both of which we're going to get into today. This is a beautiful one to start with. This is actually called a uniform distribution. Uniform meaning all the weights are the same. So if you guys took a bunch of 4-credit classes and you're trying to figure your GPA out, you just add up all you got and divide it by how many classes you have, because there's the same weight for each class. But if you don't have that, you have to adjust. So let's develop a tool that will work in every case, not just in a uniform distribution. So let's do it old school. Let's do it how we would do it old school. So we're going to put this in quotes. Actually, I'm going to do it in a different color. the way we used to do weighted means. Is anybody pissed that I called this mu instead of x bar? Did I piss anybody off? It's Thursday, you don't care, it's okay. We'll come back to why we can call it mu in a second. We'll come back to why I'm not calling it x bar in just a second. So a weighted mean back in the day, and you probably don't remember this and it's okay, we had to create a third column, and we called that the x times f column. And then we divided that by the sum of the frequency column. That was the old school way of doing weighted means. Is that fair? I mean, this is what I did with the keys back in the day, with the refuse back in the day, with your GPA. There's a whole bunch of different examples we did with weighted means. And they're great. And then I stopped torturing you and let you use your TIs, because that was a much easier way to get the answer. Now, let's adjust this for these new labels up here. X is still X, but F is now the probability of X. So let's swap out the F's with probability of X's. So it's going to look like the sum of each X value, each random variable value, times its probability over the sum of all the probabilities. So all I've done is take the F's out and replace them with probability of X's. And maybe you're getting a little bit sick to your stomach because that now looks worse than the old weighted mean, right? Until you realize that part of that equation we can ignore mathematically. Or part of that formula. JC, which one? What's the sum of all probabilities? 1. So there's no need to do that. That's extra work we don't have to do. So let's just drop that and just call it the sum of all of the random variable values times their probabilities. That is not all that hard to do. All we've got to do, and we're going to only a couple times today, we're going to use technology for the most part, is we're going to take each of the random variable values and multiply it by its probability and then add them down the line. Now, I want to do it at least a couple times out because I want you guys to see what the hell's going on. And if you use technology, you'll get the exact same result, but it hides what's actually happening. And that's what I don't like. I like you to understand why it is 3.5, why the 3.5 that you guys decided on was 100% correct. But if you understand it here, you'll also get it for all the other distributions. Let's do it. So you take the first value, 1, times the probability of 1/6, then 2 times 1/6. 3, a little bit boring, Mathematically kind of boring. Because Megan's going to say, well, dude, why don't you just factor the 1/6 out? And then add up 1 through 6 to get 21. Yeah, 21. And then divide 21 by 6 to get 3.5. We can do that. I don't want to do that. Here's why. This is 1/6. That's 1/3. That's 1/2. That's 2/3. This is 5/6. And that's 1. Now that adds to 3.5. There's no secret to what it mathematically equals. I mean, that's 3.5. So the average number of rolls, the average number of pips we see per roll is 3.5. But here's what those individual components mean. Over time, think back to your projects now with probability. What does it mean to say that there's a 1/6 chance of rolling a 1 when I throw a die? What does that mean? There's a 1/6 chance of rolling a 1 when I throw a die.
That if you roll the die 6 times, one of those times will get a 1.
Add 2 words to that. There it was, on average. Did you hear what I said? And you hear why I made him say the extra 2 words? He said, when you throw a die 6 times, you'll get a 1 in one of those 6 times. And I said, add 2 words, and he said, on average, or over time. If everyone wants to say over time, that's okay too. So what you can do is, you can roll a die 10,000 times and have the line of the results in front of you, and then you can move them around and put them in order. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Because Jenny, you had 1s, 3s, and 6s. Somewhere down the line, somebody got a bunch of 2s, 4s, and 5s. We can mix your 2 together and call it good. I don't know where it was. It might not have happened in this class. It may have been the other class. It might have been 10 years ago. It might be 5 years in the future. But they're out there somewhere to be mixed together. So it's the law of large numbers. This is a relative frequency of occurrence over time. Thank you. Now, each time that happens, for the long-term average, the 1s contribute 1/6 of a pip to the overall pip total of the average. The 2s contribute 1/3 of a pip towards the average. The 3s contribute 1/2 of a pip. the 4's 2/3, the 5's 5/6, and the 6's contribute a 1 pip. Because 1/6 at a time, you get 6 pips. That's 1 pip on average. When you sum up all those fractional pips, it adds up to the 3.5 pips that you get on average per roll. That's the share. That's the share. When you adjust for the weights. Now with the uniform distribution, it's kind of boring. Scott's going to say it a different way. Duh. Every 6 pairs with a 1. That's 3.5. Every 2 pairs with a 5. That's 3.5. Every 3 pairs with a 4. That's 3.5. Perfect. But that only works for uniform distributions or perfectly symmetric distributions. So you got to be careful when you move away from that. This is a more general way of looking at it, that each random variable is contributed a certain percentage of the time. Therefore, think about your budget for your household. Right? Think about the budget for your household, how much you have to spend on average per month. Right? Those probably aren't equally spread between like the power bill, the water bill, the sewer bill, the trash pickup bill, your cell phone bill. They're not like all 1/5 or 1/4. Some contribute more to the overall bill than others. That's what you're keeping track of here. You're keeping track of the percentage of the overall that each piece contributes. So it's only a 6 for the 1, and it's 1 for the 6th, because the 6 has 6 times as many pips on it as the 1 does. Ish? We're going to keep coming back to that. How do you answer that question? No, I'm sorry. That was a good stretch I just ruined.
That's
Sorry.
okay.
Now, here's something I will never make you do. What is the standard deviation around that? Oh, before that, anybody pissed that I called this mu? Why are you not pissed that I called this mu?
It's Thursday.
It's Thursday. It's a good answer. Because that's what's going to happen. There's no arguing that is what happened. I mean, that's the distribution that is in the population. So you can't call it mu. Here's one thing I'll never have you calculate. The standard deviation of that number. So practice right now. Get this in your TI. Give me the average and the standard deviation around that average. Oh, that's little sigma. Good case. What the heck? What the heck?
That was an S. So
Sorry, it is. It's a Greek lowercase s. Thank you very much. No mistake. No, I draw it kind of wrong. It should look like that.
Okay.
Like a sideways 6 with a big long tail. So practice right now. L1, L2. Go. One more stats. Bitte. Ooh, and while you're doing that, I'm going to install the damn TI because I keep forgetting I got to do that.
I know. I didn't want to delete it.